this problem right here kind of has historical significance. If you were to go back 2,000 years ago, people thought, it just seemed logical that if you dropped an object, the heavier it was, the faster it would fall. Like, if you dropped a bowling ball, it would go faster than this calculator even. But it's not true. Everything travels at the same rate. And we know that for a fact. It was the person that really showed that was Galileo. And he did this kind of with ramps. But here's kind of how this works. And this is really how this works when you drop something from a tall object on the Earth, is it's represented by a quadratic function. And the 16, that number right there usually has something to do with gravity. And it works like this. So this is really the way it would work. So in equal amounts of time, the rate would square like this. So for instance, you start basically it would be 0 seconds. And then after 1 second, it's gone down 16 feet. And then after 2 seconds, what it's going to do is it's going to do 64. And then it's going to do that. It just sort of keeps changing based on this function right here. So the idea would be if you plugged in like 1 second, you can do this in your head. I just want to show you kind of how this works. So if you plugged in a 1 after 1 second, that would be, it would have, the motion would have gone down 16 feet. If you plugged in a 2 there, that would be 16 times 2 to the second. So that's 16 times 4, so that's 64, and so forth, okay? So that's the way it works. It speeds up as it goes down, and all objects are going to travel at the same rate. Now, if you had like a feather and you had a bowling ball, the bowling ball would go faster than the feather. That's only because of the way the atmosphere works, okay? So that's a true historical problem, okay? Now, we're going to work a little bit with this, and just kind of work on the average velocity. Our goal is to be able to find out that instantaneous velocity. And you could actually do that with calculus. You could figure out at any point in time, how fast this object is dropping from the Leaning Tower of Pisa. Okay, so what we want to do is let's write down on this next page. Let's go to the next page. And what we're working with is the function f of x equals 16x to the second. Okay? And we're going to go ahead and do average velocity, which is a real simple thing to do. If you're doing average velocity, you need to know that you're really working with a slope of a tangent line. Okay, so you need to know 2 points. Once you know 2 points on the graph, then you could easily compute that average velocity. So what you need to do, first of all, is just plug in the 2. So we're going to work out what f of 2 is. Okay, this would be how far has the object traveled after 2 seconds? So that would be, and the diagram on the previous page already has that anyway, but let's go ahead and crunch that out. So that would be 16 times 4. That would be 64 units, whatever that is. On the last page it says feet. So that's going to be represented by feet. Okay, and what this does is this gives us a point, 2 seconds, 64 feet. If you're doing average velocity, you just got to have 2 points. Then you find the slope. Okay, then we're going to do f of 3. Okay, so that's going to be 16. You're going to plug in the 3 in for x. So that's 16 times 3 to the second. That's 16 times 9, so that's 144 feet. Now, if you look at the diagram on the previous page, they've already crunched that out for you. So does everybody understand where I'm getting that? Yeah, that's just evaluating the function. So that gives you a point, 3 and then 144. Go like that. Okay? Now, if you want to find the average velocity, what you do is you just do the slope. Okay? So just the way you're used to finding a slope between 2 points, you subtract the y's. Okay? It's the change in y. In this case, it would be the change in the distance that the object is traveling, and then it would be the change in the time, 3 minus 2. Okay? That's what you work out. That would give you the average velocity between 2 and 3 seconds. Okay, so let's see. If we do that, what is 140? I should be able to do that in my head. I'm being lazy this morning. 144 minus 64 is 80. Okay, so that would be 80 over 1. And really what that would be is it would be 80 feet per second. Okay, the numerator is giving feet because it's a change in the direction, and then the denominator is giving time. Now what that means is that basically when this object drops, its velocity is changing. It's getting faster at every point in time. That's only the average of the velocity. Okay, so does that make sense? Okay, all right. A lot of times students in this class are business majors, and one of the reasons we go over a little bit of physics because it helps students understand the idea of rate of change, although we're going to look a lot more at economics and stuff. Going through velocity and stuff helps you understand the concept of a rate of change. Okay, now the next thing we're going to do is we're going to do this to help us begin to get the instantaneous velocity. So what we're going to do now on this second part is we're going to do the same thing, but we're going to do this more generically. We're going to find the average velocity when we're using these two things. 2 plus h is just a variable that we're just going to say it's some variable that's a little bit bigger than 0. Okay, so we're going to do the same thing. We're still going to do f of 2, but we're also going to need to do f of 2 plus h. Okay, and then we got to get 2 points, and then we're going to find the slope. So if you got an average velocity, you're always finding a slope. Okay, we already did f of 2. F of 2 was 64. That was already crunched out in the previous problem. So that's 64. So that's going to give us a point 264 that we're going to use when we compute the slope. Okay, now the next one, when you do 2 plus h, okay, what you're doing now is you're taking this function, 16x squared, and what you're going to do is you're going to replace that x squared with 2 plus h. Same thing, you just plug it in. So let's do that. So you're going to have 16 times 2 plus h squared like that. All right, plug it in. Now, how do you work from your background, how do you work out something like 2 plus h squared? Algebraically, what do? You write it out twice, and you multiply it out. It's like FOIL is what it is, okay? So we need to go ahead and run through the details of that. Okay, you can't multiply the 16 through that because that's being squared. You got to do order of operations. So let's just write that out twice, and then we'll kind of review how you do the FOIL. Okay, all right, so what we're going to have here then is 16, then have a set of parentheses, then let's run through the FOIL here. So if you know how to do that, you can go ahead and do that. So you need to know how to do that. First term is 4. Outside term is 2h. Okay, inside term is another 2h. Okay, and then the last term, h times h, is h to the second. Okay, so you got to multiply that out. You got to collect the like terms. Then we'll multiply the 16 through. Okay, so when we do that, to finish that up, I'm going to go ahead and do 2 more steps. I can put these like terms together to get 4 plus 4h plus h squared like that. Okay, then distribute the 16 through, and you're going to get 16 times 4 is 64. So that will be 64 plus 64h and plus 16h squared like that. Okay, so that's what we end up getting. So what I want to kind of do to kind of help you keep track of what we're doing is this is our first point right there. After 2 seconds, the ball has traveled 64 feet. This is more generic, okay? This is saying that after 2 plus h seconds, then that value is 64 plus 64h plus 16h to the second like that. Okay, so these are going to be the 2 points that we're going to be working with. And let me pause there and see if you guys got any questions about what I just did. Okay, if you want to find average velocity, tell me what you ultimately do.
Subtract?
Yeah, you find the slope, right? You do the slope form. That's what you want to get in your mind as you do a slope, okay? So what we're going to go ahead and do is we're going to go ahead and continue this. I'll do this to the side because I'm kind of running out of room. So you take these 2 points and you find the slope, okay? So the average rate of change is going to be this. You take the y's and you subtract those. So that's going to be 64 plus 64h plus 16h to the second minus 64. Okay, so what I just did there is I just subtracted that and that. And then you're going to see the 64s are going to cross out. Okay, then we do the same thing in the denominator. We subtract these. we do 2 plus h, and we do 2. Okay, everybody understand what I'm doing? Okay, because we worked on slope formula a lot in yesterday's class, so you want to know how to do that. Okay, now we're going to get a mathematical expression for this. Okay, so those are going to cross out, the 2's are going to cross out. So the answer on part B is the average rate of change is represented by 64h plus 16h to the second all over h. Okay, like that. Now the algebra on that's pretty basic because it included foiling and then doing a slope formula. Everybody with me there?
So you don't take out that h?
You can. Now you can do it now or you can do it later. You are correct. What you're going to end up doing, because in the next part we're going to do the limit. I was just going to wait until I do the limit, but absolutely you could do that now. Okay, everybody else okay? All right. Okay, so that would be the official answer to the average rate of change. And then what we're going to do on this is we're going to do the limit as h goes to 0 of this average rate of change. And what I'm going to try to help you understand is what this is going to do is when we do this, this is no longer going to be an average rate of change, it's going to be an instantaneous rate of change, okay? And we'll kind of begin to talk about that. Well, right now, if you plugged 0 in, what would happen in the denominator? You would have a 0, right? And if you even plugged h into the numerator, you'd have 0 also. You can probably do that in your head. You have a 0 over 0 limit, which means it's going to exist, but you need to simplify this first. So some of you already noticed that you can take out those h's, right? So what we're going to go ahead and do is factor an h out of the top. Now you could do this in your head. There's more than one way to do this. I'm just going to take a factor of h out. I don't need to worry about taking anything out for 16 and 64. So I'm just going to do this way. And then I'll have that. And then all over h like that. So, you can multiply that out in your head, and then you're right. The reason I do this, anytime you're doing one of these limits that has a 0 over 0 form, you want that thing to go away. That's what's causing the problem. So what you can do now is cross that out, okay? And then you're going to end up having the limit as h goes to 0 of 64 plus 16h like that, okay? Now, what do you do to close it off? It's not 0 over 0 anymore, so what do we do? Just plug in the 0, exactly. So you just plug that in right there, and then you would end up getting, you can do that in your head, 64 plus 16 times 0 is equal to 64. Okay, now what that's going to end up being, in the context of this problem, is that's going to be the exact velocity at 2 seconds. That's not an average rate of change, that's the velocity. So what this is really 64 feet per second is the velocity. We call this the instantaneous velocity. And we're going to talk about what that is in just a minute, okay? I want to just kind of use this example. And that's going to end up being what we call it doing a derivative in calculus, where we do differentiation, which we're going to talk about. So the idea is if you take the limit of that expression from part B as h goes to 0, you get the velocity at that particular instant. And what's going to happen in this diagram is that's going to continue to change. So you could pick any value of x, any time, and you could figure out exactly how fast it's going at that point. And it's calculus that you have to do that. Okay, does that make any sense? Okay, all right. If it doesn't yet, I think it will begin to when I kind of define this. So I'm going to go ahead, and the next thing is we're going to look at what we're really doing with an instantaneous rate of change, okay, and kind of define that. So the first thing is you have to know what a tangent line is at a point on a graph, okay? So what I want you to do is just draw some sort of a graph that looks something like that. Just sketch something out like that, okay? And I want to explain what a tangent line is, okay? First of all, if you have a secant line, we've already talked about what secant lines are. A secant line just means you do what? You just connect any 2 points on that graph. Okay, that's what happens. Now, if you do a tangent line, it's only going to go through 1 point. And the idea is going to be that if you slide this point infinitely close to the other one, then you get what's called a tangent line. So you can think of a tangent line as a secant line where the 2 points are almost the same. Okay, you can make it as close as you want to. So let's put like a dot right there for example. Okay, if you wanted to draw a tangent line there, really all you're doing on a tangent line is you're just picking a point that's infinitely close to it, and then you're connecting the dots. So that tangent line is going to be like that. Just think of it as a secant line where the points are infinitesimally close. All right. So here's another one. Let's put one dot here. Okay, let's say that we want to find the tangent line there. Okay. All right. So the tangent line doesn't go like this. A lot of times students don't know this as well as they need to. It does touch one point, but think of it more like this. Think of a point real close to it, and then connect the dots. If you connected the dots on that one, you would get a tangent line that's horizontal. Okay, like that. And that's because there's a low point in the graph. We call that a minimum, and that's going to be a place where that tangent line looks like that. So that's the idea. Just take two dots close together, and then you got a tangent line. All right, does everybody understand that okay? Okay. All right. Now, go ahead and draw your tangent lines on the next page. Okay, I gave you 4 dots. All you need to do is just pick a dot that's right next to it and then connect them. Okay, and then that's the way to draw a good tangent line. So I want you to just take a minute to do that. Then we'll kind of begin to develop the idea of what an instantaneous rate of change is, and then a derivative. Okay. And in today's class, we're going to kind of get into a lot of algebra. Now, the way I usually teach students to do this, again, is just put a dot right next to it somewhere and then connect the 2 dots. Then you got it. If you do it that way, you can't go wrong. There's a tendency sometimes for students to want to draw a tangent line like that. So if you think of it the way I'm showing you, you won't make that mistake, I don't think. Okay, so it just kind of go like this one. This tangent line would be going through kind of like this. It might be sloping just barely negative. This one at the top, that one's probably going to be perfectly horizontal, like that. This one right here is going to be sloping upwards, kind of like that. And then this one here, see it's at a maximum. That one's probably going to be horizontal like that. So that's how you draw tangent lines, all right? All right, everybody got that. There's nothing to that, but you want to think of the idea of those points being, 2 points being very, very close together, okay? Now, what I'm going to do is, this is a super important formula in calculus that involves a limit, okay? When you're finding the slope of a tangent line, this is the formula that does that, okay? And this thing right here, we talked about that last time. That's called the difference quotient, okay? And a lot of you have a background for what a difference quotient is. So I want to show you where this comes from. So what I'd like you to do is, let's just draw something kind of like that, okay? Just a rough sketch of just any function. We're going to call that f of x, okay? All right. So what we want to do on this is, let's say that we have 2 points on here. Let's say that we have this point right here, and let's say that we have this point right here, because I want everybody to get this diagram drawn correctly on here. So what we're going to do is, we're going to take this first point, and you want to go straight down to the x-axis, and we're going to call that point x equals a. A just represents whatever the x value is, okay? Now what we're going to do next is, you want to look at that function value. So if you go over to the y-axis, okay, this point right here, what that's going to do is, that's going to give you f of a. All right, that's the function value of a. So you got a, you got f of a. Okay, so that gives you a point. That means this point right here is a comma f of a, like that. All right, does that make sense? Okay, just kind of generally how you name function values. Okay, now what we're going to do is this. We take a number that we call h, and we make h be some positive number. Okay, it's got to be greater than 0. So what we're going to do is, we're going to go over h units from a, and then we're going to define this next point like this. So this next point, you're going to go straight down like this, okay? And think about this. If this is A, and that's H, what is that going to be? A plus H, exactly. All you're doing is making A get bigger by H. So this point right here is going to be X equals A plus H. Okay? Right? Now the next thing is this function value. What's the function value going to be of this one? F of A plus H, right? Okay. So we have F of A plus H like that. So that's how that goes. So that means that this point right here has a X value of X plus H, and it has a Y value of F of A plus H like that. All right, so these are the 2 points that we're going to be looking at, is this right here. Okay, that's the setup. Does that make sense to everybody?
A plus H?
A plus H, not X plus H. Thank you. Okay? All right, everybody okay with what I'm doing so far? Okay? This is just showing you where this formula comes from. Okay, so here's what we do. All right, we know that we can get a secant line by just connecting those 2 dots. And if we want to find the slope of the secant line, that's going to go like that. That's what we've been working on. Let's go ahead and find that slope. So when we do that, you're going to subtract the y's. You're going to use the slope formula. So you're going to get f of a plus h minus f of a. Okay, you'll get that. And then you're going to subtract the x's, which is a plus h minus a like that. And we actually did this in the last class when I kind of went over a difference quotient. Okay, so I want to try to put it all together.
Would the bottom be in parentheses, the a plus h, or you just
you don't have to have it in parentheses. The only time you really need parentheses when you subtract is if you had something like more than one thing there. Okay. I'm only subtracting one thing, so it's really not necessary. Okay, all right. So let's go ahead. The only thing that happens on this problem now is, of course, the a's cross out. So you want to do that. So what we have is we have really the average rate of change, like we learned, is f of a plus h minus f of a all over h. Okay? And of course, that's in that formula. We already looked at that. Now, this is what we're going to do on this. Here's the idea, and listen to this real carefully. The reason we're going to do the limit as h goes to 0 is we're going to make h go to 0. All that's going to do is move this point closer and closer and closer to that. Remember, I said a tangent line is when you connect 2 dots infinitesimally close. And we can make h as small as we want, as long as it's positive. Okay, so what's going to happen is this secant line is going to turn into a tangent line. And when you get a tangent line, that's what gives you an instantaneous rate of change. On that last problem I did, that's what we did, is we found how fast that object was moving by doing that limit. Does that make any sense? See, if you have a secant line and you move those points together, you get a tangent line. And that gives you the slope of the graph at that particular point in time. Okay, that's what instantaneous rate of change is. So what we do then is to find the instantaneous rate of change. I'll just abbreviate like that. Then all we do is just do the limit as h goes to 0 of that difference quotient. Okay, and then that we're going to find in a little bit here. We're going to work on derivatives today. That's what a derivative is going to end up doing, is it's going to give us the slope of a tangent line. Okay, so that's kind of the abstract, the theoretical development of that idea. Does that make sense to you guys? Or when I was a calculus student way back when, this didn't make sense to me immediately. You have to kind of think about it a little bit. But that's the idea. Yes?
You know, when you said the 2 points as they come together, what is that? You told us.
It ends up giving you a tangent line, and the slope of a tangent line is what an instantaneous rate of change is. So the key difference is an average rate of change is a secant line. An instantaneous rate of change is a tangent line. But the idea is, with a limit, we can make h get as small as we want to. We can make it 0.0000 infinitely 1. And for all practical purposes, you got a tangent line, right? That's the idea. So that's what's happening on the problem, okay? All right, let's move on from here. Now, I'm going to go through and we're going to begin to look at a derivative here a little bit. So this is your instantaneous rate of change definition. The idea that you want to get in mind is this. When h gets smaller, this secant line turns into that tangent line. That's the idea, okay? From your background, sometimes students, if they're in high school geometry, learn about a secant line and a circle. A secant line connects two dots. A tangent line of a circle just has one dot on it. So that's analogous if you've learned that before. Okay, now one of the things I want to kind of do on this is I'm going to just open up this applet. The internet's got all kinds of applets, and I'm going to redo what I just did quicker. And you can kind of look at this, and once this thing loads up, this also is a good way to show you what an instantaneous rate of change is. This takes you kind of step by step through the idea we just did. So what we're doing is, if we're finding what we call a derivative, we're looking at the slope of the tangent line. A tangent line on this would go straight through like that, okay? So the way this is kind of developed is like this. Just like we did before, you have A, you have f of A. Then you move over h. H is going to change, and on this applet I'll be able to change that. Okay, so we go to A plus h. Then we go to f of A plus h, okay, like that. Now here's the idea. This is what you can do on this applet that's kind of cool. Right now that's an average rate of change. Now watch what happens on this. H right now is 1, but as h is getting smaller and smaller, isn't that secant line getting closer to the tangent line? That's the idea. So when you get that all the way almost to 0, then you got a tangent line. So that's how you make an instantaneous rate of change. To me, that's a real good way to show it. Okay, what do you think? Okay, so h can get smaller and smaller. That's the idea. So eventually, we end up getting that slope of that tangent line right there. Okay? All right, so let's go back and kind of finish up what we want to do on the bottom here. So what we're going to do is let's work with one example kind of like this, and then we'll start the rest of the section. We're going to talk about how to find derivatives, okay? And then we're done with that. We're going to learn the easier way to find derivatives, okay? Okay, so first of all, let's go ahead and do we're given this function, okay? And what we want to do on this particular function then is we're going to find the slope of the secant line through these 2 points, okay? Let's go ahead and do that. So the first thing you need to do is you need to do f of 1. This was easy enough to do in your head, so you would just have 2 times 1 squared, so that would be 2. So that's going to give you a 0.12. Okay, if you find a secant line, it's all about knowing a slope. Finding a slope is knowing 2 points. Okay, so we got that. Okay, do f of 2. Okay, so that's going to be 2 times 2 squared. That's 2 times 4, so that's going to be 8. So that gives you a 0.28 like that. Okay, and then we'll be able to get the slope of the secant line. Okay, so the slope, I'm going to write m for slope. M is usually what we use for slope, of course. Then go ahead and do your slope. So we're going to do 8 minus 2 over 2 minus 1. So that looks like 6 over 1. So that gives a slope of 6. Okay, we've already done that several times. So everybody should have that down by now. Okay, now what we're going to do is we're now going to end up finding the slope of a tangent line on this now. So if you're doing that, now you have to change this. We're going to find a slope of a secant line that goes through these 2 points. So instead of doing 1 and 2, we'll do 1 and 1 plus h. Okay, so we do the same thing. Okay, f of 1 we already got. That was 2. We had that in the previous problem. Okay, let's go ahead now and do f of 1 plus h. And we did this a few minutes ago, so it'll be very similar to what I did a few minutes ago. All right, how do you find f of 1 plus h? Well, you go to your function, and what do you do with your function?
Square it.
You replace the x with 1 plus h, right? Then you square it. Okay, good. So you just write down, go to the function, do what it tells you to do. That's 2, replace the x now with 1 plus h, and then square it like that. All right? Okay? Now you need to FOIL this, so you need to be totally confident with your ability to do that. So go ahead and do that. Okay? And if you know how to do that in your head, you can. I'll go through that a little bit here at some point. Let's go ahead and multiply that out. Okay, now I like to go ahead and just sort of FOIL first. So if I do that, I'd have 1 times 1 is 1. 1 times h is h. Inner term is 1 times h or h. Then the last term is h times h or h squared. Okay, that's FOIL, right? You guys know how to do that, right? Okay, I never know. All right, so this is going to be 2 times 1 plus 2h plus h to the second, okay, when you collect the like terms. Okay, now multiply the 2 through there. Okay, so that's going to be 2 plus 4h plus 2h squared like that. Okay, so what you get out of this then is you get 2 points. Okay, this point 1 f of 1 becomes the point 1, 2. Okay, the second point becomes this. 1 plus h, and then this thing. 2 plus 4h plus 2h to the second like that. Okay, everybody got the algebra down? Tell me, you're foiling and that kind of stuff. Is that cool to everybody? Okay, because I don't know. All right, now let's find the slope. Okay, so the slope is going to be subtract the y's, subtract the x's. So the y's are 2 plus 4h plus 2h squared, and then minus 2, like that. Okay, then do the x's, so that's going to be 1 plus h minus 1. You always got stuff cancels out when you do it this way too. So we would end up getting, for this slope, you would have 4h plus 2h to the second all over h. Okay, and yeah, you can go ahead and factor the h out and take that out if you want to. Okay, you can also do this way. If you want to, instead of factoring the numerator, you can also just go 4h over h plus 2h squared over h like that. You can do it that way if you prefer to. And if you do it that way, that's going to cross that out, leaving 4, and cross one of those things out, leaving 2h. Okay, so that's the expression that we have for the slope of the secant line. Okay, and remember, h is some positive number. Okay, does that algebra look reasonable and fairly simple to everybody? Okay, because that's what you're going to get into in this class, a lot's algebra. It's going to get a lot heavier than this. Okay, so here's what we do to finish this up then. Okay, we're going to find the slope of the tangent line as x goes to 1. So what that means we're going to do is we're going to do the limit as h goes to 0 of this expression. Okay, see, we built this around 1 anyway. In the previous problem, we did 1 and we did 1 plus h. So that just means 1 plus h, when we make it go to 0, then that becomes a tangent line. Okay, all you got to do on this is just plug in. Plug in 0 for h, so that's going to give 4 plus 2 times 0, so that's going to give 4. So that would be the slope of the tangent line. Okay, that gives it to you. All right, that's what you do to find the slope of the tangent line then. All right, now let's do an equation of a tangent line. Okay, if I want you to find an equation of a tangent line, then you need to work with this formula generally. It's the point slope formula, y minus y1 equals m times x minus x1 like that. Okay, now what this is this 4 is the slope of the tangent line. So that's going to plug in there. Okay, we already have a point. If you go to the previous problem, we had a point 1, 2, and that's where we're interested in the tangent line anyway, is at the point 1, 2. Okay, so that means what we're going to do is you're going to plug the 4 in there, you're going to take the x value of 1, and then you're going to take the y value of 2. Okay, we're finding equation of a tangent line at when x is 1. That's the idea. Okay, so when you do this, you're going to have y minus 2 is equal to 4 times x minus 1 like that, and you're going to solve this for y. Okay, so this should be pretty basic algebra. You'll have y minus 2 is 4x minus 4. Okay, add 2 to both sides to get y by itself. Okay, and then that will give me y equals 4x minus 2 as your equation of your tangent line. Okay, so what we just did is we now have the ability to find a slope of a tangent line at any point on a graph. Okay, is there anything I need to clarify on that? Now this will probably make real good sense to you once we do the graph, because that's what I'm going to finish up the problem. is we're just going to do a couple of things on the graph then. So let's graph. Let's see, we were doing the problem y equals 2x squared. And let's just use our calculator on this, and then let's also do 4x minus 2. I mean, this is one that's easy enough to do without a calculator, but it'll be kind of one of the things that when you do a tangent line's equation, you can tell you're right visually. So get your calculator out. And let's go like this. So put in 2x squared. What is 2x squared going to look like from your background? What is that? It's a parabola, right? It's opening up, so it's going to go like that. And then our tangent line, of course, is a line. So go ahead and put that in. And then when you go to y2, just put in the tangent line. Okay, 4x minus 2 like that. We want to graph both things out, and then this should help you to understand what we just accomplished. Okay, for a window, let's just do standard window. So you can always go zoom 6. You can just type the 6 if you want to get that graphed in a standard window. Okay, like that. So what you're going to have is you're going to see your parabola, then you're going to see this tangent line coming out. Okay, so if you look at what's coming out on the calculator, does that look like what you would expect the tangent line to look like when x is 1? Right, x is 1, that looks like a perfect tangent line. Okay, so this is what I want you to put on your graph. We had the point 1, 2. Let's just label that point as 1, 2, like that. You also have a point on the parabola that's negative 1, 2, and then just sort of sketch it. It's good enough if you just kind of sketch that. Okay, and then if you did your tangent line, well, you can do the tangent line without a graphing calculator. What's the y-intercept? Negative 2. What's the slope? 4. So you're going up 4 over 1. So if you go ahead and do that, it'd go like this. So you'd have a y-intercept, then you would go up 4, right 1, and then you'll have a pretty good tangent line like that. Okay, so basically that graph should hopefully help you to understand what we just did. And what this is that's the slope of the graph when x is 1. Now the slope of that graph, isn't the slope of this graph always changing? Like right now, what's the slope of the graph right there? What is the slope if it's like this? 0, right? Right? Now what's happening to this slope? Isn't it getting steeper and steeper and steeper? It's always changing because a tangent line gives you the slope of the curve at a particular point. Okay, that's what and we're going to do tons of stuff with this. This is a real big deal when you're looking with rates of change. Okay, so let's look at now kind of beginning to find a derivative of a function. Okay, now a derivative is what it's doing is it gives you a function that will allow you to find the slope of the curve at any particular point in time. So we're going to learn how to do derivatives. That's going to be the big thing we're going to be working on the rest of today's class and then Thursday. And into next week we'll be working a lot with derivatives. So it's the same kind of idea. The thing that's a little different, first of all, when you see f prime of x, okay, we call that a prime. If you hadn't seen that before, that's what we use to represent a derivative. And what a derivative is it's a formula. It's a function that will give you the ability to find the instantaneous rate of change at any point in time on any curve, okay, as long as you have the derivative exists. So it's the same formula that we just got through doing for finding an instantaneous rate of change. Okay, a couple of vocabulary items here. When we find a derivative of a function, we call that differentiation. For now, we're just going to focus on this notation. F prime of x means find the derivative. Okay, so if I say find f prime of x, that's what you're going to do. Okay, so let's go to the next page, and I'm going to kind of take you through how you find derivatives. And this is using the definition. And then when we get to the next section here in a little bit, then I'm going to teach you the ways that, like this problem right here, you will be able to figure this derivative out in your head eventually. But you got to start by working with the definition. Okay? Okay, let's do this one on the graphing calculator, just kind of speed through this a little bit. Okay, so if you're going to do this one, let's go ahead. And if you put a 1/4 in, you could do a decimal 0.25, or you can do this. If you put 1/4 in, you need to have that in parentheses if you're going to do it that way. because if you don't, it won't be graphing the right thing. Then you want to put in x to the second like that, okay? So be sure you put it in that way, or just put 0.25x squared, okay? Go ahead and graph it in a standard window, so you can go zoom 6. And I want to go to the table because I want to try to do this fairly accurately. So what I would do is let's just go second graph to open up your table of values, and then just plot some points. Okay, so I'm going to go kind of backwards with this too here. Let's find some good points. I just need to find a few. So it looks like we have negative 4, 4. Okay, got that point there. Then it looks like I got negative 2, 1. I got 0, 0. I think I may be off on that a little bit. Oh, negative 2, 1. I plotted one of those wrong. Okay. So just look at your table and pick the ones that don't have decimals in it. So let's see. Negative 2, 1. 0, 0. And then it's symmetric. So you'll have 2, 1. And then you'll have 4, 4. And so forth. And that's probably good enough. And then you can connect those dots like that. Okay, so just kind of connect that into something like that, and that'll be good enough. So we got a pretty good accurate graph there. Okay? All right, so what we're going to do is and I'm not going to do the tangent line at x equals, I'm going to do the tangent line at just x equals negative 2 this time. Okay? I don't want to repeat it twice. Let's just do one. Okay, so if you were going to do the tangent line, okay, I want you to just estimate it. Go to negative 2, which is this point right here. X is negative 2. Now, how would the tangent line be sloping? Would it be sloping down or up or what?
Down.
So you would expect that to be a negative slope, right? Just kind of sketch it, okay? We're going to try to see how accurate we are when we do the derivative. So I'm going to go through and just kind of sketch it, something like that. It's probably going to look something like that. Okay, the y-intercept looks like maybe it's 0, maybe it's negative half. We're going to find out precisely, but that's the idea. Okay, all right, so we're going to go ahead on the next thing. This is what we want to do. Go ahead right now, this is important, and write down this formula, because you need to see this formula when you're applying it and find the derivative. So anytime you're doing a derivative, at least for now, we're going to bypass this later. You're doing the limit as h goes to 0 of f of x plus h. Whoops, that should be not an a, that should be an x. We're going to do x now. F of x plus h minus f of x all over h like this. Okay? And some of these things get pretty complicated algebraically. This one's not too bad. Okay? So we're going to go ahead and put this together now. All right, so what we're going to do is we're going to take the function, and we're dealing with this function right here, 1/4 x squared. Okay? If you're going to do a derivative, the first thing you got to know how to do is how to set up this thing we call the difference quotient. I usually teach it this way. Go ahead and just put like 2 brackets all over h like that. Okay? Because what you're really doing in this formula is you're doing this. F of x goes there. What is f of x? That's what I gave you, right? Then what goes here? F of x plus h. The only difference between f of x and f of x plus h is what happens to that x. It turns into x plus h, okay? So you want to put this in like this. Put your function here. Whatever it is, whatever I give you goes there, okay? Now f of x plus h is just going to be the same thing, 1/4, but that changes into x plus h squared. So the idea is this thing changes into that thing, but everything else is the same. Okay? Does that make sense? Sometimes students do not see how that's set up for some reason. But just change x to x plus h, and that's what f of x plus h is. Yes?
What does f time mean again?
That just means the derivative. And a derivative is a function that's going to allow us to find the instantaneous rate of change at any point on the graph. Okay? Or the slope of the tangent line at any point on the graph.
That prime is the f to the first.
It's not a first power. That means a derivative. Okay? And in calculus, we see this a little bit later in this class. You'll see like f double prime, that's called a second derivative. That just means you do the derivative again.
And that would be f2.
Yeah. Okay, like we just say double prime, then we can go to triple prime, which we won't even see in this class.
You know, the mark above the F, isn't it angled a little bit?
It is, okay. I may not be doing it perfectly, but it's kind of like that, I guess. Okay, but that's a derivative. It's kind of like an apostrophe, sort of. Okay, now let's go ahead and let's work this out. Now it's just time to do algebra. And what you're going to do all the time on this is do this x plus h squared thing. So I'm going to just kind of do this at the side, and I'm going to teach you, if you don't know this, how to do this in your head. Because you need to know how to do this in your head. Now, you got two choices. You can write it out twice and FOIL. Okay, you can do it that way if you wanted to, okay? Or you can do it this way. The way that you do this in your head is you just do this. You just square the first term, okay, x squared. Then you square the last term, and you do that. That's easy enough. However, you have a middle term. The way you get this middle term is you multiply those two things together, which is xh. Then you double it. Okay, so you double that xh to get a 2. So if you FOILed it, that's what you would get. And you're going to do that so often in calculus, you want to know how to do x plus h squared in your head. Just square the first, square the last, multiply them together and double it. That's how you do it. That's the shortcut, okay? So now let's go ahead and let's put this together now. Okay, so keep bringing down your limits so you don't forget about that. So we're going to have 1/4. Okay, now the x plus h squared, we just worked that out over there. So that is x squared plus 2xh plus h squared, like, whoops, hold on, that needs to go like this. That's going to be plus h squared minus, and then this second part stays the same, minus 1/4 x squared all over h like that. Okay, and then we're just going to do algebra, and what's going to happen is you're going to have a 0 over 0 limit, and somehow that h in the bottom is going to cancel. It always will if you do this right. So I'm going to distribute this. So next thing that you want to go ahead and do is just distribute the 1/4 through there. Okay, so you're going to have limit h goes to 0 of 1/4 x squared. Okay, then you're going to do a 1/4 times 2. When you do a 1/4 times 2, that's 2/4. So that's a half, right? Reduce the fraction. Okay, so that's going to be 2/4 or 1/2 xh. Okay, and then 1/4 times h squared is going to be 1/4 h squared like this. And then just bring down the rest of the problem. Okay? All right, everybody with me? Okay, I really did a little FOIL, and then I just distributed. What do you see happening? Okay, good. You're always going to see stuff canceling. Okay, so you're going to have that. All right. Now what you're going to have is if you plugged in 0 right now, you would have 0 in the denominator, and wouldn't you also have 0 in the numerator? Okay, so what you want to do is you want to factor this h out of the top before you do the limit, because you want it to cancel with that h in the bottom. So let's do that. Okay, just bring the limit down. So the limit h goes to 0. Okay, we're going to have h times 1/2 x. See, I'm just kind of factoring out of this piece right here, plus h, or 1/4 h, sorry. Okay, and only take the h out. You don't have to take anything else. That's a waste of time. So just do the 1/4 h like that all over h. Okay? All right, now what happens?
You cancel out h.
Cancel out h, good. Then what?
Then you have...
h goes to 0. Yeah, you're fine. Okay, so you go ahead and now let h be 0. Okay, so if h is 0, what does this whole mess become? 1/2 x. Okay. Okay, so we get 1/2 x. Because see, that thing right there is going to go to 0. Okay, so what you end up having is the derivative of this function is 1/2 x. Now that's how you do that using the definition. By the end of class today, you'll know how to do that in your head. Okay, but we've got to learn it this way first, okay, before you do it the other way. So most of that's an algebra problem. So you have a question?
Basically, the derivative for like right here, it's just kind of like solving for the limit, right?
Yep, it's finding the limit of the difference quotient with h going to 0.
Okay.
And what it's doing is it's giving you a formula for the slope of a tangent line at any point on this curve. If you look at that curve, that tangent line's always changing, isn't it? So like for instance, if x is 0, a half times 0 is 0. That means the slope of the tangent line is 0, which it is. Okay, if x is 1, 1 half times 1 is a half. So the slope of that tangent line is a half. That's what it does. It's a function that gives you a rate of change.
Where did the 1/4 go when we took it out? Because I know you said h out.
Okay, I did right here take an h out. Okay, so I have h, the 1/2 x,
Right.
the 1/4. Now what I did is, it's not that the 1/4 went away, is the h's went away, right? And then I plug in 0 for h. And that made that whole thing go away.
Gotcha.
So you're left with 1/2 x. See, the last move on the problem is to let h be 0. Okay, everybody okay?
H's that are left. 0.
Yeah, that's what wiped that out. Okay, that's the idea. That's the way it always works out. Okay, so let's go ahead and do one more piece of this problem here. We're going to go ahead and find f prime of -2. Now what that means is you're going to find the slope of the tangent line when x is -2. So all you got to do is take that -2 and plug it into your derivative formula. So you do 1/2 times -2. Okay, what's that give you? -1. Okay, so let's go back and let's look at the graph I had you draw. Okay, that's a negative slope for sure, right? Okay, look at your graph right here. It looks like if you went down, if you have a slope of -1, it's down 1/1. So we're pretty close, right? Okay, it wasn't perfect, but now you could draw it perfectly. Okay, so the slope of that tangent line is down 1/1. That's how that goes. Okay, so that's a rate of change is what that is. Okay? All right, so that's kind of the beginning of how you begin to learn about derivatives and what they're doing. Now, these are going to get a little more complicated algebraically as we do these today. All right, is there any question?
So the f prime of 1 would be a half, right?
Exactly.
Okay.
Yeah, and see this formula right here gives you the derivative always. Like if you were looking at 10, way over at x equals 10. 10, 1/2 of 10 is 5. So you would end up having a slope that's up 5/1. You can kind of tell that by looking at the graph.
And if you go over 1, y it looks like it's at 0.5, so it matches out.
Yep, exactly. Yeah, so it's a formula that's giving you a rate of change. Yes.
So why would you have us find both x equals -2 and x equals 1 when they're going to end up being the same answer?
Oh, it doesn't matter. I can have you find a value of a derivative anywhere.
Yeah.
Okay.
But I was just curious why, like on our homework, it seems like we do a lot of stuff like that where it's extra.
Where it's more than one.
Yeah. It's
I think part of the repetition on that is you want to see how it's changing at different points.
Yeah, but you're going to get the same answer.
On which one?
For the prime, or that f prime x. So, like,
Oh, you mean f prime of 1? F
Yeah.
prime of 1 would be a half. It'd be a different answer. So if
oh,
you're,
never mind. I screwed up. I read.
Oh, you're fine. You're fine. Okay, so if you're doing f prime of 1, that would be a half times 1, so it'd be a half.
Mhm.
The idea with having students do several different points is to see how the tangent line slope is changing over and over. It's not always going to be the same. Yeah.
So the derivative, when you're working out the derivative, you're trying to find the rate of change of the slope. Or you're trying to find
The rate of change of any point on the graph. And that rate of change is a tangent line. It's a slope of a tangent line. You can draw a tangent line on just about any point on a graph. There's some exceptions to that, but it's giving you that rate of change, which is a slope. A slope is a rate of change. Okay, so that's what you're doing. Okay, now let's do this one. This one right here is actually a little easier. So I'm going to go ahead and do this one, and then we'll probably do maybe crunch out the example 9, then we'll take a break. And then the rest of these we're going to do a little I'm going to do a couple of these that are a little harder. Okay, so let's go ahead and let's graph this one. We don't need to have a graphing calculator on this one. So we got a line, right? So go ahead and just graph the line. Well, you know you got a y-intercept of 4. You have a slope of 2. So that's up 2/1. Okay, you don't need a calculator for this. So just go over 2, up 1, maybe a couple of times, and then connect your dots, and then you got your function. So this time the function is a line instead of like a parabola like on the last problem. So let's label that g of x. Okay? Yeah.
I have a question. This is probably a dumb
That's fine.
question, but how come it changes like f of x, g of x, h of x? Is it just
Okay, because I'm varying that on purpose, because it can be anything.
Okay.
A lot of times students get the idea that a function's just always f. It can be anything. Okay? Like in business, you might have c of x to represent the cost of x.
Right. Okay.
Or
So
things
it's
like
just
that.
kinda getting used to it.
It's varying that to get you used to that. That's why I'm doing that. Okay? Okay, let's do a tangent line at, let's just pick, this time let's just do x equals 1. Okay? All right, now if you were going to x equals 1, you would be right here on this point right there on the graph. How would you draw a tangent line if it's already a line?
Parallel line?
Well, it would be parallel, but wouldn't it just be the same line?
Yeah.
Okay, it'd have to be. And it wouldn't matter where you are on this graph, right? If you wanted to draw the tangent line there, wouldn't it be the same? See, this thing right here has a constant rate of change. That's when you have a line, its rate of change is always the same. It's always up 2 over 1. That slope is always the same. Okay? So you're going to end up having that result when we do the derivative. So your tangent line, just kind of draw in something like that. You are correct, it is parallel, but it's the same line. Okay? All right, let's do the formula then. Go ahead again. When you're learning how to do these derivatives, it's a good idea to just write the formula down first of all. So it's limit h goes to 0, f of x plus h minus f of x all over h right there. Okay, so that's it. Now let's go ahead and put this together. So the whole key on this for students is sometimes students struggle getting this put together right. And then sometimes there's some struggles with the algebra. Okay, so let's get this put together. I recommend you do it this way. You don't have to, but you can just immediately put it together. This seems to help. So what goes here in this problem? Tell me what goes there.
2x minus 4.
Right, 2x minus 4. What goes here? What's the only difference?
2x plus h minus 4.
Good, okay. Function, and then only difference is 2x plus h. So you slide in the 2x minus 4 here. Okay, then this thing is going to change to x plus h. Okay, so over here you're going to have this. You'll have 2 times x plus h minus 4 like that. Okay, has everybody got that? Sometimes students just don't see that good for a while for some reason. That's all you do. One of them's the function, the other one, the x becomes x plus h. Okay, now it's algebra. Okay, so what we want to do here is you're going to have stuff canceling out. So we're going to distribute here. So that's going to be 2x plus 2h minus 4. Okay, be careful with your algebra because I deal with a lot of that when I teach calculus. How does a minus affect everything here? Changes sign, so it's going to be minus 2x plus 4, right? Okay, be careful with stuff. You don't want to mess up on stuff like that. So minus 2x plus 4 over h. What do you see happening? Lots of stuff cancels, doesn't it? Okay, so that's algebra moves. Now that's going to cancel. Okay, like that. Whoops, I don't know why I put an h there at the end of that. That should be a plus 4. Okay, and that looks like the 4's cross out. So what you're going to be left with is the limit as h goes to 0 of 2h over h. What happens to the h's? They cancel. They always do if you do these right, okay? So what would be the limit of just a number 2? 2, right? Because after all, the function y equals 2 is a horizontal line like that, so it's that. Okay, that's it. Well, let's see if that makes sense. We said if we drew a tangent line to a line, it would be the same line. Tell me what the slope of this line is. 2. Ah, we got the same thing. Surprised? I hope not, okay, because it's the same thing. Okay, so what that's saying, if the derivative turns out to just be a number, that's going to mean that the rate of change is always the same. So that's what you get for your derivative. Okay, does anybody need any clarification on the algebra or the setup of that? Because this is real important that you get this down. You okay? Okay, you got a weird look on your face. But
It's just, I gotta remember not to, for 2x minus 4, don't put x plus h.
right, that's the key thing is this is what I give you. And then this is what changes.
Right.
Whatever x is here is going to change to that. Everything else remains the same.
So the function, it'll only be the function on the second part, and then you're just going to add extra on the first part.
Exactly. That's what f of x plus h minus f of x means. Okay? All right, so here's what you have. So on part B, basically if you were doing f prime of negative 2, the answer would be 2. Okay, we already got it. And if you were doing f prime of 1, that would also be 2. Okay, it's always the same. So that's the idea. That's how you find a derivative of a line. So see, you'll be able to do these problems real fast. So if I had, say I had f of x equals 11x plus 2. You know what the derivative is? 11. That's a type of problem. Boom, boom. You know the derivative immediately. Okay, that's our derivative rule we're going to start looking at a little bit later today. Okay, I'm going to go ahead and do this example 9. I'm not going to do any graphing on this. I want to just see if you can do the derivatives okay now. Okay, so what we're going to go ahead and do this time is we're going to go ahead and when we do f prime of x, I'll start again with the same definition. It's always the same. Limit h goes to 0. F of x plus h minus f of x over h. And this formula right here transformed the world. I like sometimes students, I know you're business majors and stuff like that, but this idea comes from Isaac Newton's development of calculus. This is really kind of what changed the world with technology, his ability to make discoveries in physics and electronics and stuff. That would be probably in my top 10 list of greatest mathematical formulas of all time. Okay, it's a big one. Okay, and it's a major formula that's wrapped around calculus. Now this time what we're going to do is just get the derivative and then evaluate it at negative 2. Okay, so watch this carefully. This one, the algebra will be a little heavier. This is probably a good test question, and even the last problem I did, because this is sometimes these problems get really heavy algebraically. Usually my Calc 1 class, I might have them do something a little heavier than I do in survey. Okay, so let's go ahead and put this together. Now again, this is the way you want to do this. You want to take a lot of room up on your paper too, so it's not all crammed up and stuff like that. Okay? All right, now this is what I always try to get students to make sure they do. Tell me what goes there.
2x squared minus 3x plus 1.
Right, what I gave you. What's going to go here? What's going to be the difference? The x's turn into x plus h. Good. Okay. So I always just tell students to start this way. Put your function there, whatever I give you. Now, over here, just make that small change. We're going to go to x plus h to the second minus 3 times x plus h plus 1 like that. So you got to make sure you have that set up down when you do that. Okay. So we got a bunch of algebra that you need to do. All right, I'm going to do this little piece one more time because you seriously want to know how to do this in your head. Okay, you'll do it so much you'll get it memorized. Okay, so again, what you do is you square the x, square the h, right? Then what? Multiply them together to get xh. Then what? Double it. Okay, that's how that goes. Okay, or write it out twice in FOIL if you forget how to do that in your head. Okay, so I'm going to bring this over like this. Keep writing your limit down. Don't be lazy about that, because if you forget to write it down, you may forget to do the limit at the end of the problem. So what we're going to have is 2 times. I'm going to replace this x plus h squared with x squared plus 2xh plus h squared. And as I'm going through this, I'm just going to do basic algebra. So I'm going to distribute. That's going to be minus 3x minus 3h, like that. Do the basics. Then you got the plus 1. Okay, tell me what happens here with this minus. Oops. So it changes. Minus plus minus. Students mess up on stuff like that a lot, so be careful with that. So that's minus 2x squared plus 3x minus 1. It's all over h. When you do these problems, write lots of steps. Don't do things sloppy. Just do it step by step. Okay? Next thing I'm going to do is we're going to distribute the 2, and then you're going to start finding a whole bunch of things are going to cancel. Okay? So let's do this one more kind of key step. That's going to be 2x squared plus 4xh. Okay, and then plus 2h to the second like that. Okay, then just bring down the mess. 3x minus 3h plus 1 minus 2x squared plus 3x minus 1 all over h. And I'll pause there a minute and let you catch up and see if you got any questions, because that's the key. If you get to that point, don't make any algebra mistakes. You're likely that you're going to get this right. Okay, everybody following along okay? Okay, this is a great test question. Usually quadratics aren't too hard to do. So what happens? Just go through and cancel everything that cancels. Okay, that cancels. 3x's cancel. 1's cancel. In fact, I want to show you something, and this is actually important, is notice that everything's left over has an h in it, doesn't it? Okay, it always will. And then that's going to allow you to cancel that h out in the bottom. So I'm going to go ahead and write just kind of one more key step. I'm going to highlight what's left over, and then what you want to do is just factor that h out of this. And you can do this in your head too. I kind of like to make sure students know how to do the factoring. So what I'm going to do is just take the h out of what I highlighted in yellow. So that's h times 4x, 4x plus 2h minus 3 all over h. And of course, what happens? H crosses out. Okay? Now, what's the last move that you do? Got to do the limit. So when you do, and you can do this in your head, all that's going to do is change this to 0. So what's the answer? 4x minus 3. So that's the derivative. The derivative is a linear function. So now you just have 4x, you can do this in your head if you want to, minus 3. That's going to give 4x minus 3. Okay, so that's the conclusion you get. That's the derivative, and that's going to give you the ability to find the slope or the instantaneous rate of change at any point on that. So we'll close the problem off by doing f prime of negative 2. And what that's going to tell us is our answer to this problem is going to tell us the slope of the tangent line to this curve when x is negative 2. So what do? You just plug it in there. So it's 4 times negative 2 minus 3. That's negative 11. Okay, so that's what you get. Okay? That problem right there to me is kind of the level for testing purposes. I want you to be able to manage this type of thing and probably the two before that. We're going to go ahead and take a break, and then the ones we're going to do to finish up are a little harder with algebra. I'll give you some of those on homework because you need to get, usually students got to get better in their algebra when they're in calculus classes. So I do that for that reason. Then we'll learn the simple ways to do this. Some of you who have had calculus before, I'm going to show you real quick how you learn to do this ultimately. What you do is you just bring the exponent down. 2 times 2 is 4. Then that x becomes 1 lower. That's 4x. This part right here, minus 3. So what you're going to learn a little bit later in class today is how to do this derivative in your head so that you don't have to do this, which is kind of cool, isn't it? Okay, that's what we're going to learn how to do. Kind of works like this. If you're doing like x to the third minus x squared, if you're doing the derivative in your head, here's how you do it. 3 goes down 1, 2, like that. Okay? That's what we call the power rule. We'll work on it a little bit today. And that'll keep you from having to do this. But you got to start somewhere. Okay? All right, let's do 10 minutes. Moving on to this next example here. We're going to look at a function that has a cube in it, and we're going to find the equation of the tangent line. And if you find an equation of a tangent line, well, you got to use this formula. But when you find m, you might want to make a note that m is going to be found by doing f prime of x. Okay, that's the derivative right there. So you have to find the derivative on this problem before you do anything else. And that's the big part of this problem. If you find an equation of a tangent line, is that derivative will give you m. Okay, so this is what we're going to work on. So let's kind of go through this carefully. Go ahead. And again, write your formula down. And you need to know this formula. I'm not going to give you the formula like for a test. You need to know this. Okay, it's fundamental. Every calculus student's got to know that. It's such an important formula. Okay, let's set it up. Okay, so this time what I'm going to do is we're going to work with this function. So I'm going to kind of do the same thing I've been having you do, is maybe just draw a couple of parentheses or brackets and then get it put in. Okay, so I want to make sure everybody's got this on track now. Tell me what goes there. 1/2 x to the third. What goes here?
1/2 x plus h to the third.
Right, the same thing, but the x becomes x plus h. Okay, so you have 1/2 x to the third there, and then here you have 1/2 x plus h to the third. Okay, so that's what you got to deal with. Now, the hardest part of this problem, it's not that it's hard, it just takes a little bit of work, is you're going to have to work with that x plus h to the third. Okay? All right, we used to teach shortcuts on this, but nobody does that in college algebra anymore. But you're not going to have to worry about taking this any time bigger than the third power. So just kind of over at the side, you find yourself a little bit of room somewhere, and let's just write that out 3 times. Okay, and then let's multiply this out. And the thing on this is, a lot of times I'll see students just try to do this all in one step, and you really can't. What you really have to do is you can put together the first 2 if you want, and then you can FOIL that. Or you could even do that shortcut that we did, that we've already done several times. So what I'm going to do is let's go ahead and just one more time, let's just FOIL this out. Or you can do the shortcut. If you do the shortcut, you're going to get x squared, h squared, and then what's in the middle?
2xh.
2xh. See, if you memorize that, boy, you speed yourself up a lot. So that's what that's going to be. Then bring down the x plus h like this. And you just have to crunch it out, okay? So what I'm going to do next here is I got to multiply like this. Whenever you encounter that, it's just that everything here has to be multiplied by everything here. So you got to do 1, 2, 3, 4, 5, 6 multiplications. That's a distributive property. So you've got to make sure that everything's accounted for. Okay, and let me know if you don't follow this. Okay, the first thing you would have is x to the second times x is going to be x to the third, because you're adding exponents. Okay, then you're going to do x squared times h, which is x squared h. Okay, so that takes care of that. Now do the same thing with the 2xh. So we're going to do 2x times h. That's plus 2x to the second h. X times x is x squared. Okay. Then do the 2xh times h. So that's going to be 2x h to the second. Okay. Now I'll run back through this one more time before I'm finished with this. Okay. Now we're going to do the h squared. So now we do h squared times x is h squared x. Then h squared times h is h to the third. Okay? And sometimes this is a background issue that students don't have down very good. So I'm just doing this times this, this times this, this times this, and so forth. Does everybody see what I'm doing okay? 6 multiplications, okay? All right, now do you see anything that looks like a like term? That looks the like, doesn't it? That's the same, okay? These are the same also. Those are, hold on, do I have a mistake in there? I think I do somewhere. That's why you guys are looking at me funny.
Choose xh squared.
x2h.
I think I'm okay. I need an x. Where should my hx squared come from? Yeah, okay. Let me do it one more time in my head real quick. X to the third, x squared h, okay, 2x squared h, 2xh squared. That should be okay. Okay. All right, I was just thinking there was a mistake. So let's put everything together. Okay, so let's see. X squared h. Yeah, these are the same. These are like terms. I'm not seeing this right. I'm just seeing these things backwards. Okay, these things kind of pair together like this. So this is 3x to the second h, and it doesn't matter which order. And then these go together. They're still h squared x, so it's still 3 of those. So I'll just write this as 3h squared, and then this is plus h to the third. That's what you should get. Okay? And that's not a hard thing to do, but you got to be careful about that when you do that. Okay, now I'm going to take this and go back to my problem and just kind of replace it over here. I'm going to replace that here. Okay, and then we'll have a lot of stuff canceling out like we always do. Okay, so this is going to be 1/2. Now put in this thing that I wrote over here at the side. You're going to have 1/2 times x to the third plus 3x squared h. Okay, plus 3x h to the second plus h to the third, and then you still have this piece minus 1/2 x to the third like that all over h. Okay, so that's the hardest part of the problem is what I did on kind of the side. And it's just multiplying. Okay, any questions on that? Okay, all right, well distribute now. Okay, go ahead and distribute, do this part. Distribute that 1/2 through everything. So you're going to have the limit h goes to 0 of 1/2 x to the third. What the heck? Okay, so it looks like what I have is I have 1/2 x to the third plus 3/2. Okay, that's 3/2 x to the second h. Then go this way, that's going to be 3/2 hx to the second, and then 1/2 h to the third minus 1/2 x to the third all over h like that. Okay, so same idea except algebra. Do you see anything canceling? Okay, those cancel, right? Okay, here's the other thing. Notice that everything that's left over has an h in it, doesn't it? So what are you going to do with the h's in this part right here? Going to take it out. You're going to factor it out. Okay, so you want to do that. Okay, so the next step we'll have limit h goes to 0, and then we take the h out to have 3/2 x squared plus 3/2 x. That goes down to h now. And then the last thing, the third power would go down to h squared like that. All over h. Then you can wipe out the h's like that. Okay? So always factor out. That's what you almost always do at those problems because you want that h to come out.
And that's h third, right, to the third power?
No, because I took an h out. I factored an h out. So if I take an h out, that goes down one. See how those exponents went down one on the h's? Okay? All right, what's the last step? Okay, anywhere you see an h, okay, anywhere you see an h, and there's two places where you see an h, okay, those will go to 0, right? Okay, so after we've done that then, looks like what we'll have is 3/2 x to the second, okay, and that is the correct answer to the problem. Those things are going to go away because h goes to 0, so what you'll have for your derivative is 3/2 x to the second. Okay, and that's the right answer. I can tell by, I know the shortcut, so I know that's the right answer. Okay, that's an example of something that's a little bit more difficult to do algebraically, but eventually we'll kind of bypass this and start doing it a simpler way anyway. Okay, what's the hardest part of that problem? Algebra, not calculus, okay. All right, so let's do a couple other things on this. So we want to go ahead and we're going to find the equation of the tangent line at this point right here. So we got this point. That's a point on the curve. So when we do the tangent line, you're doing y minus y1 equals m times x minus x1. So we want to go ahead and do that. Okay. All right, so here's what you got to do with this. First of all, I'm giving you a point. So that just means the y value is 4. So that goes there. The x value is 2, that goes there. Okay, how do you find m?
Yeah, that's the...
You plug into the derivative, right? Okay, the key thing is take this x value, which is 2, and plug it into your derivative. Okay, because that's what the derivative does is it gives you the slope of that tangent line. Okay, so what you have is you have f prime of x is equal to 3/2 x squared. So what we're doing is f prime of 2. Okay, because that's the point that I'm interested in, the x value is 2. So you do 3/2 times 2 to the second.
So you don't just put 3/2 x squared in the equation?
No, you got to, the slope is a formula. It is a number. So you have to plug that 2 in there to get the exact slope of the tangent line. You don't want to plug the 3 halves x squared in for m. You want to plug the value that you get from that when you get the slope. So that's going to be 3 halves times 4. That's really 12 over 2. So that's equal to 6. So the 6 goes in like that. Okay, that's how that goes. Okay, so the big part of this problem is the derivative. The rest of it is not hard algebra. Okay, now let's go ahead and crunch that out. So we have y minus 4 equals 6 times x minus 2. Okay, go ahead and just multiply that out, solve for y. So that's going to be y minus 4 equals 6x minus 12. Okay, multiply it out. Add 4 to both sides. Okay, and what you're going to get as a result there is y equals 6x minus 8. So that's the equation of the tangent line, like that. Okay, and that gives you basically the tangent line, which is going to give you a rate of change at that particular point. Okay, now we're going to do this on the calculator. So get your calculator out. We're going to put in this function. And you want to put this in like this. If you have a half, you could use a 0.5, or you can use the 1/2 in parentheses. X the third, and then put in the 6x minus 8 like that. Okay, and you can kind of use this to help you understand what we just accomplished on the problem. Okay, and I'm just going to put 0.5 in. So 0.5, x to the third, and then I'll put my tangent line in, which is 6x minus 8.
How do you do to the third?
What's that?
How do you do to the power of 3?
Okay, like this. Okay. Okay, I'll put in the 0.5, put in your x, and here is your exponent key.
Okay.
This we call it a caret key. So you just do that, and then you'll either, if you have an older calculator, it'll put the caret, then you put a 3. Newer calculators automatically take it up to the exponent. So you go like that. Okay. Do that in the standard window. Okay, just go zoom 6. Okay, you're going to get a cubic function. Whoop, I got something in wrong. Anytime this happens, you get an error, go to the go-to thing, and it'll tell you what your mistake is. See, I didn't even put my 0.5 in. Okay, so it's 0.5x to the third. Okay, and then I got to take this thing and delete it. Let me just put the whole thing in again. Okay, are you getting a function that goes like this? Okay, you should somewhat. Okay, there's your cubic function coming out. And let's see if it looks like we got a good tangent line. Okay, we're looking at the tangent line at the point 24. So if you did this on your calculator, if you type trace 2, that should give you a perfect picture of what I want you to see. Okay, here's your function. That's the tangent line going through that point 24. See, that's it. We did it perfectly. You can tell by the graphing calculator that it's right, just by the way it looks. Okay?
So, again, y1 and y2, like what? So y2 is just the derivative, and then y1 is the original function.
In this formula, you're talking about this formula right here, right?
Right.
Okay. In this formula right here, x1, y1 is the point where we're looking at the tangent line.
Right, but in that little box that you wrote.
Those are just the 2 lines, the 2 graphs.
Oh,
those are the two graphs. Those are the two graphs.
Okay.
Yeah. Yeah. Okay. All right. Does that make sense?
Right.
Okay. All right. Just make a real quick sketch. This doesn't have to be perfect. The key thing is I want you to see this on a calculator. So let's put like the 0.24. And if you graph your line, well, you know you have a y-intercept of -8, right? So if you have a y-intercept of -8, just go down 8. And then you can connect the dots like that. That's your tangent line that's coming out on the graphing calculator. And then the rest of it you can just kind of sketch. I'm okay with that on this because I'm wanting you to see visually what's going on. So you have a point going like through that. The graph kind of does something like that. Then it kind of does something like that roughly. But that's what I want you to see. Okay? Okay. Yes, go ahead. I can't hear you. I'm sorry. Oh, the 2. The 2? I'm not sure where you're looking at here. Are you looking at where I did this? Okay, I gave you this point. So x1 is 2. I gave that to you. and y1 is 4. That's a point that's on the graph of 1/2 x to the third.
Yeah, when you put it in there, the sheet for the, where it says 3/2 x squared, you put it in there, so you know what it says.
You talking about up here?
Yeah.
Okay. Well, let's see. That came from,
I didn't get the 6.
I multiplied the 6. Okay, the 6. Here's the derivative. Okay, that's when we did that limit. Now I plugged 2 in to there. That's what I did over here. Yeah, so see, you got to get the derivative and then plug the x value in, and then that will give you the slope of that tangent line. Right. That's it. Okay?
I got 2 of these.
Okay, thank you. Okay, all right, let's move on to, I mainly want to kind of go down to a couple of things on this next page, and then I want to finish up with just 2 more derivatives of things that are a little harder algebraically, because you need to get into that. Okay, so here's kind of the idea is, let me see if you guys are processing this by now. Okay, these 2 formulas right here are different. We've got that, and then we got this. What's the difference between those 2 formulas? The limit, okay? So if you don't have the limit, what would this formula be doing? What do you think the right answer is? What is that finding? It's finding an average rate of change, right? So that's what that is, okay? All right, what is the next one finding? There you go, okay? That's what I'm wanting you to kind of see is, you basically, when you do the limit as h goes to 0, you're turning a secant line into a tangent line. So I want you to know that, okay? I wrote down just some common kind of things that you'll see. Certainly like as for business students and stuff, you'll see rates of change in all kinds of contexts like revenue and cost and stuff like that. Okay, so these are some of the different types of things that you'll see when you're doing a derivative. So it's a rate of change. So like the rate of change of something's distance is its velocity. Velocity is a derivative. Okay, how does velocity change? When you drive in your car, how does your velocity change? It speeds up and goes down. What is that a change of? Acceleration. Okay, so basically acceleration is a rate of change of velocity and so forth. Okay, and these are things like this. How does money in a bank change? Well, the interest rate may change. Okay, so when you're dealing with rates of change, you're typically dealing with a derivative. Okay, all right, let's finish up this section with these 2 examples. And these things right here will challenge your algebra background a little bit, so I'll be kind of interested to see how well you know how to do this kind of thing. Now, again, probably next week, we'll learn how to do this derivative a little simpler, but we want to kind of do a couple of more like this, and then you won't see me doing this difference quotient anymore. Okay, let's go ahead and just set it up. We have the limit as h goes to 0. I'm not going to write down the formula this time. I want to just kind of write the setup like that because you want to make sure you have this down. This is one thing students struggle with sometimes. All right, once again, tell me what goes there. 1 over x minus 1. What goes here? 1 over x plus h minus 1. Okay, change the x to x plus h. So your function goes there. Okay, what goes here is 1 over x plus h minus 1. And you can have a x plus h in parentheses, but it doesn't matter if you leave it off. Okay, right now, this would be a 0 over 0 limit. Okay, it's a little harder to see that in your head, but basically, if h was equal to 0, wouldn't these things in the numerator just cancel out? Okay, so it's 0 over 0. So the limit exists, but you got to do some sort of algebra to make this happen. So sometimes students do not have good backgrounds for this. The idea is you want that to go away and you want that to go away. If you want this to go away, you just multiply by x minus 1 so it cancels out. But if you do that, you have to do the same thing to the bottom. If you want this thing to cancel out, you just multiply by x plus h minus 1 so it does. But you got to do the same thing to the top and bottom. So what I want you to write on your paper is just kind of write this like this. But let's draw like a big bracket around this. And we're going to write x minus 1 times x plus h minus 1. You got to get rid of both of those things, so you got to multiply that whole numerator through by that. And then the denominator also has to be multiplied by the same thing. And what I'm going to try to train you how to do is how to do this in your head so you don't have to write a lot of steps, okay? It's all a matter of how you look at this. So you're going to do a distributive property through this. So this thing is going to multiply by that. Just block that off in your mind for a minute. If you multiply this times this, tell me what's going to happen. That and that are going to cancel, right? What are you going to be left with? 1 times x minus 1, right? Just see that in your head. Just don't even look at that. Cancel, cancel, and then write what you're left with, okay? Learn to do it that way so you don't have to write all these steps on your paper. Okay, so let's write that. And then if you don't get that, I'll do it one more time. Okay, so this part right here, so that's going to cancel the x minus 1. So you're going to have 1 times x minus 1 or just x minus 1. Okay? Now do it this way. Block this off and tell me what happens when you multiply that by that.
X minus 1 cancel.
They cancel. What are you left with? Minus 1 times that, right? Okay, everybody see what I'm doing? Okay, just kind of process that in your head. So now the x minus 1's cross out. So it's minus 1, x plus h minus 1. Now the denominator is h times x minus 1 times x plus h minus 1, like that. Okay, so we got that. Okay, now one thing I want to say is do not ever waste your time multiplying the denominator out. Leave it factored, because you know what you want to happen? You want that h to go away. That's always the end of the problem. You want that to happen. So what I'm going to do is let's go ahead and just multiply out the numerator. You'll have a bunch of stuff canceling like you always do. Obviously that is x minus 1. This just changes the sign. So you're going to have minus x, minus h, and plus 1. And then write down that denominator in an unfactored form. Don't multiply it out. You're totally wasting your time and you don't want to do that. Okay? Your time's too valuable. Okay, tell me what happens. See how stuff always cancels? It always does. Okay? So that cancels, and you're left with this. Okay? Let's write what we're left with. So we have limit h goes to 0 of negative h over h times x minus 1, and then x plus h minus 1, like that. Okay? All right? Now, what happens? H is cross out. You kind of catching on that always happens? You need to. Okay, so that's going to cross out. So you're going to end up with the limit as h goes to 0 of negative 1 over x minus 1, x plus h minus 1, like that too. Okay, but I'm not done. All right, what's the last thing?
Put 0.
Okay, that's going to go there, right? Okay. Now, does anybody have a question? Go ahead.
Is it minus h because that negative got distributed?
Is it what?
Minus h.
Here, no. Because that came from way back here.
Oh, okay.
Yeah, that never changed. See, what I was doing is I was doing a distributive property right there, okay? Oh, hold on. No. The denominator just stays the same. Yeah, the denominator, that's what we multiply by, so we're okay. Yeah. What's that?
Is the negative 1 because...
After you crossed everything out here, okay, you had a negative h over h. Well, there's still a negative there after the h is crossed out, right? So you really have negative 1h there. That's why, okay? Now, what's the last step? It's always the same. H goes to 0, right? Okay, so when you do that, you don't have a limit anymore. You have negative 1 over x minus 1. Then you just have another x minus 1, right? Just block that off. That goes to 0. So that's your answer to your derivative. The best way to write this would be negative 1 over x minus 1 to the second. Okay? And then next week, I'm going to teach you how to do what we call a chain rule that'll allow you to do the problem to bypass this, and it's a little easier. Okay? Okay? So that one's a little harder sometimes for students algebraically. I want you to know how to handle fractions and how to get rid of them. Yes, you got something?
So I'm just having trouble setting it up from the very beginning.
Okay.
You said, okay, so can you explain just the first step?
Yeah, okay, so the setup, and I think you're okay with getting it set up like in tech.
Right.
Okay, you got f of x goes there, and then that changes. So what you see in black there is the original problem. So what I was trying to do is get rid of x minus 1. If I want it to go away so I don't have a fraction, I have to multiply it by that so it'll cancel.
Okay.
If I want to get rid of x plus h minus 1, and I have to, we don't want a fraction. We want to get rid of fractions. then you multiply by that to make it go away.
So you're multiplying both denominators of the top.
Exactly, yes.
Okay.
And the thing is, you're distributing that through the whole numerator, and whatever you do to the top, you have to do to the bottom of the fraction.
Okay.
You have no choice.
Right.
Because if you do, if you don't do that, you're changing the problem.
So it gets rid of it on the top, but then it leaves it on the denominator.
Right, so now notice after you've done that, you don't have a fraction in a fraction anymore.
Right.
Then that allows you to go through, and then from there, it's pretty simple where things cancel and stuff.
Okay.
Okay? Okay, let's do one more with the square root, and we'll see if you know how to do this okay. All right, now what I'm going to do this time is something just a little different. Okay, we could go ahead and find f prime of x, then plug in the 4, or we can go like this. This time what I'm going to do is we're going to do this. Okay, I want you to write down this formula. So what we're going to do is f prime of 4. Okay, so we're going to say the limit as h goes to 0, but this time we're going to say f of, instead of x plus h, we're going to say 4 plus h, because that's what x is. Okay, I'm telling you what x is based on the directions of the problem. So let's say f of 4 plus h, and then minus f of 4. Okay, and you can do that. I mean, you have two choices. You could either find the derivative and then plug the 4 in, or you can plug the 4 in now. Okay, it's probably a little easier to just do it this way. Okay, so let's put this together and see if we kind of understand how this goes now. All right, so let's go through. We do this kind of the same way. Okay, and we're going to put that all over h like that. Okay, all right, now watch this real carefully. So what goes here is just whatever f of 4 is. Okay, so if we want to find f of 4, you got to go to your function and you got to plug in the 4 for x. Okay, you have to. Okay, so that would be square root of 4 minus 1. That's 2 minus 1, so that's 1. Okay, so what's going to go there is a 1. Now we're going to get a numerical answer out of this problem doing it this way. So instead of doing f of x, I'm doing f of 4. Okay, everybody with me there? Okay, now what's going to go here is f of 4 plus h. Okay, if we do f of 4 plus h, all that's going to mean is go to your function, and where you see that x, you're going to replace it with 4 plus h. So that's going to give square root of 4 plus h minus 1. And that's what's going to go in here like this. So you're going to have square root 4 plus h minus 1 like that. All right? So all I'm showing you to do on this is instead of f of x plus h and f of x, you're going to have f of 4 and f of 4 plus h. Does that make sense? Okay, now let's go see what happens on this then. Okay, I'm going to go ahead and do a little algebra, and there's a little algebra in your background that you're going to need to know how to do. So this is 4 plus h minus 1, and let's see, that should be another minus 1, so that should be a minus 2. You can go ahead and do that in my head. Okay, so minus 1 is minus 2, all over h like that. Okay? Does that look different? Same idea. Okay? Now, I want to see if you can see that this is a 0 over 0 limit. Okay, if you replaced h with 0, wouldn't this thing right here just become square root of 4? And that would be 2. 2 minus 2 is 0, right? It's a 0 over 0 limit. Okay, so you have to do something. Okay? What you do in this case is, and in your background, maybe you've done a little bit of rationalizing before. I don't know, it just depends. That's why I'm doing this problem. So what we're going to multiply by is what we call a conjugate. So you multiply by the same thing, 4 plus h plus 2. Okay, then we do the same thing to the denominator. We have to do the same thing, 4 plus h plus 2 like this. Okay?
Why are you doing plus 2?
Okay, you'll find out in a minute. Sometimes students have no background for this in this class, more so than a regular calculus for science majors. But we call this a conjugate, and when you multiply it out, the radicals are all going to go away. That's what's going to happen. So if you see something like a radical minus something, then you change that sign. That's called a conjugate. Okay, some of you have had that in your background, some of you haven't, maybe have forgotten it. So watch how I do this carefully now. I only have you do this a couple of times on homework, and then I don't test over this either. Not in this class. I do in calc for science majors. So what I'm going to do is just the denominator, you're going to have 4 plus h plus 2. Just write it down, okay? Don't multiply it out. Never multiply the denominator out, because what are you wanting to happen to that h? You want it to cancel. Hopefully you've caught on to that, because that's a big deal when you're doing this. Now, what I'm going to do is I'm going to FOIL this out, and I'm going to do this kind of at the side carefully. You can learn to do this in your head, so it kind of goes like this. When you multiply the first term, okay, the first term would be these. You're going to have the square root of 4 plus h squared, and we'll talk about what you do with that in a minute, okay? Then you're going to do the outside term. You're going to do this radical times 2. If you take 2 times a radical, that's going to be plus 2 radical 4 plus h. Okay, that's your outside term. Now do your inside term. Your inside term is negative 2 times this. So that's going to be minus 2 times square root of 4 plus h like that. Okay, then do your last term. Negative 2 times 2 is minus 4. Okay, so what I'm doing is I'm foiling. Okay, I'm doing this times this, which gives this. This times this gives that. There's your inner term. And then that's your outer. Does that make sense?
Wouldn't that be minus 2 square root of 4 plus h, not just minus?
Yes, thank you. That's a 2. Okay. All right. So what happens? These cancel out. That's why your question is, why did I multiply by the plus 2? That's why, because it made that happen. We want the radical to go away. Okay. From your guys' background, do you know like what happens if you take the square root of x squared, for instance? That's x. Anytime you take the square root of something squared, it undoes the square. Square roots are the opposite of squaring. So what do you think this thing's going to be? 4 plus h. Okay, and then the minus 4 comes down. Okay, so you get 4 plus h minus 4 like that. Okay, that's again algebra background issue. Okay, I always tell students when I teach it like a Calc 1 or this class that the vast majority of what you struggle with in calculus, most students do, is not calculus, it's algebra. So this is background stuff that you got to know how to do, okay, because it's going to show up, okay? So now, notice what happens. 4's cross out, okay? Then you're going to be left with the limit as h goes to 0 of h over h times square root of 4 plus h plus 2 like that, okay? Then what happens? H's cancel out. See, they always do, don't they? I hadn't done a single problem where that didn't happen. So you go ahead and cross those out. That'll leave you a 1 in the top. So now what you end up having is you have the limit as h goes to 0 of 1 over square root of 4 plus h plus 2, like that. And then you got one more step, and then you're done. So what's always the last step? That goes there. Don't forget about h goes to 0. We're going to get a numeric value on the problem. So you'll have 1 over square root of 4 plus 2, because that thing goes to 0. That's going to be 1 over 2 plus 2, so it's 1/4. So that is the rate of change of this particular function at that particular x value. Okay, that's probably the most difficult algebra thing on a limit that you'll have to do. Okay, I don't test over this. I do test over this in my regular Calc 1 because those students, probably it's a little more important for them to know how this happens in other situations. You are going to encounter this kind of thing, though, when you do what's called the quotient rule and the product rule when you're learning derivatives. So you need to work on this kind of algebra skill to get stronger with it. Okay, you see what I mean? Okay, so lots of foiling, lots of factoring. Got to know, and students always end up knowing their algebra way better after they take calculus than if they just take algebra alone. That's the way it is. Okay, let me talk a little bit, finish up. This last thing's real simple. I want to close off with this. Then we're going to do 10.5. I'm just going to teach you some of the basic rules and kind of get you going on that because those things are real easy to learn, don't take much time. Okay, so first of all, a function is going to, we say it's differentiable if the derivative exists. Sometimes a derivative does not exist on a graph, and I'll explain that then. So we say if a function's differentiable, then it's also continuous, okay? And I'll explain this, on this last page that we're going to go to in a minute. I'm not going to worry so much about this yet, but I want to kind of explain this part right here. If it's backwards, if a function's continuous, then it doesn't necessarily mean it's going to have a derivative. What I want you to do is I want you to draw this diagram right now below this problem so that you have something to kind of refer to. Let's do something like this, okay? And let's draw a graph that looks like something like this. And say we have a function, that's f of x, and it looks something like that, okay? And let's say this point right here is x equals a. Okay, now we talked about continuity, continuous, yesterday. Okay, does that graph have a break in it anywhere? So that graph's always continuous, right? Okay, but the thing is, if you're going to have a derivative, what a derivative is it's a slope of a tangent line. I want to ask you a question. How would you draw a tangent line to this kind of thing? I mean, would it go like this? Would it go like this? Would it go like this? Remember I said a tangent line's like 2 points infinitely close to each other. But the thing is, if you put a point, if you put your 2 dots there, then the tangent line would be going up like that. If you put your dots like this, then the tangent line would be going like that. You can't draw a tangent line if you have what we call a sharp point. So the derivative doesn't exist there because it's impossible to draw only one tangent line. Does that make any sense? You got a sharp point, that tangent line can't be narrowed down to one value, okay? That's the idea. So although this graph is continuous, there's no derivative that exists there. Okay, so what I want to kind of finish up with is showing you graphically how you can know when something doesn't have a derivative, okay? So this is kind of what you look at, okay? So when is a function not differentiable, okay? It's going to be not differentiable when you're not continuous. So if you find a place where a graph's not continuous, there's no derivative there either. It's impossible to have one, okay? Our textbook calls a corner, I usually call them a cusp. Sometimes textbooks just call it a sharp point. So if you have a real sharp point like that, the derivative doesn't exist there, okay? And then the other place would be a vertical tangent line. Now here's why this is the case. So if you had something kind of like this, let's say that you had a graph that did something like this. Just make yourself kind of a little sketch kind of like this. Let's say that that was your function f of x. And let's say that I wanted you to draw, that's not the best graph, I wanted you to draw a tangent line right there. How do you think that tangent line would go right there? It'd go straight up and down, wouldn't it? What do you know about the slope of a line if it's vertical?
Zero.
No.
Undefined.
That's why I'm asking. Undefined. Okay? The slope of a vertical line is undefined, and since the derivative is a slope, if that slope's undefined, then there can't be a derivative. Okay, so it'll go like that. So vertical tangent line, that point right there, what we would say is not differentiable there. So your derivative would not exist there. You're not going to have a rate of change. In fact, the differentiable is what I meant to put there. So your rate of change is actually infinite. Okay, that slope is infinite. Okay, that's the idea. Okay, so this last page here, I want to, this is real simple. Okay, it's real simple to learn how to do this. So I'm giving you a graph. We'll just do these together, kind of close off here. We want to find everywhere we're not continuous, okay? So we learned this in yesterday's class. Tell me what x value where that graph is not continuous. At 1. Every place else is good. Nice and smooth everywhere else, okay? So we would say we're not continuous on or at x equals 1. Okay, that's the only place. Okay, how about the derivative? We've got to think about, now what a derivative is it's a slope, it's a tangent line. You've got a nice tangent line there, but you don't have a tangent line there. There's no way you can draw a tangent line there because you've got a big break there. Okay, so you're going to be not differentiable at x equals 1 also. Okay, if you're not continuous, you're not differentiable. That's a guarantee. Is there one of those sharp points anywhere in here?
Yeah.
Yeah. So you're also not differentiable there. You are continuous there, but you're not differentiable. Okay, so you'd have x equals 1, x equals 2, that's where that goes. Okay, now I'm not going to have you do the sketch of the derivative. We do that in Calc 1, but we don't do that in a business calc class. Okay, that's how that goes. Okay, all right, just go ahead and fill out your answers on, don't do C, but just fill out your answers on this next one here. It's the same idea. Okay, may even have the same answer. How many places is this one not continuous? Just one. What's the place it's not continuous? X equals 1. How many places is it not differentiable? 2. Okay? If you're not continuous, you're also not differentiable. Where's the other place? Sharp point. We call that a cusp, a sharp point. Our textbook calls it a corner. Same answer. Okay? That's it. Okay? All right. Does that make sense? Okay.